Hello everyone, my name is Rajan Arora and welcome to my course ASP.NET Core Web API Best Practices. I have been working with and teaching students how to be productive with .NET for the last 10 years, and that is really my motivation for sharing tips and techniques with you. My hope is that after watching this course, even if you have building APIs with ASP.NET Core for a while, you will take away a few new tips or techniques. Web APIs are fun and easy to build with ASP.NET Core, but they are more distinction than you might expect. And building them to be fast, secure, consistent, and maintainable can be a challenge for many teams and developers. In this course, we are going to cover best practices for building web APIs using ASP.NET Core. Other courses cover the basics and the syntax. This course will show you how to design your APIs properly, leveraging both built-in features and third-party libraries. Some of the major topics that we will cover include things like which HTTP verbs should you use for various operations, how do I design my API route structure, what do I need to consider when it comes to securing my API, how do I keep my API code consistent and maintainable, and what's the most effective way to test my APIs. By the end of this course, you will be able to build web APIs with ASP.NET Core that are well organized, easy to maintain and secure. And what's more, your application will include a suite of integration tests that prove it. I hope you will join me in learning how to apply best practices to improve your ASP.NET Core web APIs. Hello everyone, this is Rajan Arora and welcome to my course ASP.NET Core Web API Best Practices. I have been building applications with .NET for over 10 years and I regularly help teams building better software. In this course, I am going to share with you many of the practices that I have learned over the years, some through my own hard-won experience and many I have learned from others along the way. Before we begin, a quick note on the version used in this course. This course was created using the displayed version of ASP.NET Core, .NET and Visual Studio. This course is 100% applicable to the versions of ASP.NET Core, .NET and Visual Studio that you see on the screen now. Web API standards and best practices do not change frequently. What is applicable using today's framework and tools typically applied just as much to previous versions of web APIs built with .NET. Of course, newer versions of this framework are going to be released and you will find update versions of this course hence once they are released. Now, let's talk about why you should care about best practices. According to Merriam-Webster, a best practice is a procedure that has been shown by research and experience to produce optimal results and that is established or proposed as a standard suitable for a widespread adoption. This seems like a reasonable definition to me. I know many other experienced members of the community dislikes the term best practice and refuse to use it, claiming there are no best practices because it always depends on context. As an experienced developer, I can appreciate others' love for the phrase "it depends." However, there really are many standard practices that should be used in the majority of contexts, and I will do my best to point out the trade-offs involved wherever it makes sense. The goal is for you and your team to build better software by leveraging the wisdom of many other software developers while understanding why a particular practice makes sense. The goal is not to turn you into robots blindly following instruction because some self-proclaimed experts said so. Some of the things we will learn as best practices are covered by actual standards. Much of the time, these are described in RFCs related to the HTTP protocol itself. Standards exist to codify industry practice and help ensure consistency between applications that will communicate using common network and infrastructure. Some of the practices will relate to less rigorously controlled community or commercial specifications like the Open API specification. And some of the guidance comes from experience. Some things I have learned the hard way and many things I have learned from others in my career. In either case, the goal of sharing this experience and the context in which it applies is to help you avoid making the same mistakes as others. This will free up a lot of your time so that you can make your own new mistakes. What are some of the benefits of following standards and practices established by industry, community, and experts? First, one of the main reasons to follow standards and best practices is to avoid confusion and surprises. When we minimize oddball approaches, custom techniques, and one-off solutions to problems that already have well-known established solutions, we make our APIs easier to use and easier to maintain. We can also improve productivity by having a consistent approach to building web APIs that typically will mean writing less code, since standard policies can often be applied consistently and even automatically across the code base. Having less custom code within each API endpoint means future changes to policies will be faster and easier to implement as well. All this leads to fewer bugs in our code and in the code of client who consumes our APIs. The less duplication we have in our code, the more consistent our interface and our ability to apply policies to all our APIs, the better we will be able to serve our customers and ship higher quality softwares. Finally, security is more important than ever, and following best practices for building secure web applications will reduce the likelihood of leaving known security vulnerabilities in your code. And when malicious clients interact with your APIs, you will be better able to detect and deal with them. Okay, you are sold on best practices now. So let's get started. The next module covers the design of web APIs mainly from the client's perspective. What do your APIs look like and how do clients call them and deal with the results? Then, we will look at the models used by your API. What I will sometimes refer to as the wire protocol, since it describes the data that travel over the wire and frequently wirelessly as well these days. Of course, since this is a ASP.NET Core course, you will learn some of the many ways in which you can build APIs using ASP.NET Core. You will also be able to decide whether to use patterns like mediator, as well as choosing synchronize or asynchronize appropriately for your endpoints. We will cover some other practices related to different features that many web APIs share as well. We will dedicate an entire module to web API security. Honestly, this could be an entire course on its own. But you will learn some of the most important topics here. And I didn't feel that this course would be complete without at least covering some of the primary practices that every API should consider. Finally, you will learn how to easily test your web APIs so you can be confident that they are working properly. You will be able to run this test as part of your automated build, which will help ensure bugs don't creep into your production environment. Up next, we will get started with web API design best practices. So let's begin. Hello everyone and welcome to the course. In this module, we are going to look at best practices for the high-level designs of web APIs. We will be focusing on rules and standards that, if you follow them, will result in a more consistent interface for your web APIs. That means your web APIs client as well as your future team members will be more familiar with this standard behavior and constraints, resulting in improved productivity and fewer bugs. Here is a quick overview of what we are going to cover. We will start with a look at Roy Fielding's popular REST architectural approach and some related concepts like resources that are often useful for any web API, even one that doesn't strictly follow REST. Next, we will review a number of HTTP verbs and talk about how they are meant to be used. Many experienced web developers are still surprised by some of the expected behaviors of standard HTTP verbs. So, if you have been using a web for decades, it may be worth a review. In a similar manner, HTTP defines a number of status codes, quite a number actually. We will focus on the ones that are most applicable to web APIs and describe when you should return each kind of status codes. We will also cover some bad examples, things you should avoid doing if possible and why. Finally, we will look at ASP.NET Core response types and how they map to status codes as well as some alternatives to using them. Roy Fielding published his dissertation Architectural Styles in the Design of Network-Based Software Architectures in 2000 for his PhD in Information and Computer Science at UC Irvine. In it, he described an architectural approach which operates on representations of resources using hypermedia. Few papers have had a great impact on the design and architecture of web APIs as Fielding's work has. This is a best practice course, so our focus is more on coding practices than background information. But a couple of moments will help make the advice on practices make more sense. Let's quickly review what REST is, what it isn't, and some useful concept we can take away even if we don't choose to fully adopt REST as an architecture of choice. REST simply stands for Representational State Transfer. Simply put, it is an architectural style for building distributed systems based on hypermedia and designed around resources. You will find many web APIs describe themselves as RESTful or RESTish. Most often, this leverage REST principle for resources but omit hypermedia. So what is hypermedia? And for that matter, what are resources exactly? Well, hypermedia is an extension of the term hypertext, which is of course the HT in HTML, hypertext markup language. Any nonlinear medium of information or data that includes the data itself, graphics, audio, video, binary data, plain text, etc., as well as hyperlinks is considered to be hypermedia. The term nonlinear is applied here because the data can be explored by following any number of hyperlinks that may be provided with or in the data. Any audio cassette tape can only be consumed in a linear fashion, while you are able to jump to any arbitrary point within a digital music file. Books, especially fiction, are typically meant to be consumed in a forward-only linear fashion, but some of the books like Choose Your Own Adventure series book allow you to make decisions and turn to a different page in a non-linear fashion based on your choices. REST architecture is built on the premises that hypermedia will be provided alongside data to facilitate navigation and interaction with the system. Clients don't necessarily need to know ahead of time all of the possible navigations available when interacting with the REST architect system. This is because the system can provide the navigation along the way using hypermedia. Now, REST is all about resources. In fact, that is what the first three letters stands for. No, it's actually not. I'm just making sure you are paying attention. Resources in REST may be any kind of object, data, or service that can be accessed by the client. A resource always has an identifier, which is a URI, Uniform Resource Identifier, that uniquely identifies that resource. That is literally what URI stands for, Uniform Resource Identifier. For example, the World Wide Web uses URIs to identify individual resources such as HTML pages, images, applications, and more. Now, a resource in REST is any information that can be named. A resource may be a document or image, a temporal service that provides information that might vary over time, like a weather forecast. It could be a collection of other resources or even a non-virtual object such as person. REST uses a resource identifier to identify the particular resources involved in an interaction between different components. And REST components do not transfer the actual resources, but instead they move about representations of resources. So what is representation? This is why a resource can be a real-world object even though we are only talking about digital communication between computers. Remember, fully half of the term REST stands for representational. No joke this time. That's what the RE stands for. REST components perform action on a resource by using a representation to capture the current or intended state of the resource and transferring that representation between components. A representation is a sequence of bytes plus representation metadata to describe those bytes. You may also hear representations referred to as documents, files, HTTP message, instance, or some variants of resources. These representations are passed between the server and the client. Now, One of the toughest problems in computer science in naming things, and that applies to your resources in your API as well. When designing your URIs for your resources, try to follow these practices. First, use noun in your URIs rather than verbs. Remember that a resource is a thing, so its identifier should reflect that. Of course, a group of things can also be a resource, and since most web APIs expose more than one of most kind of resources, the convention is to use plural nouns for almost every case. In order to specify a particular resource out of a collection of them, the specific identifier should be appended to the URI, usually separated by a forward slash. One of the main goals in your API design is that you follow the principle of least astonishment. That is, you want to avoid surprising consumers of your API with things that don't make sense to them. The less they need to learn about your API before they can use it, the better. To that end, the two most important things to remember when designing your API's endpoints are to keep things simple and keep them consistent. If you have a convention you use for a certain kind of operations, be sure that you are applying it consistently throughout the API. When dealing with resources, avoid exposing internal details. Your API resources should not be coupled to database table definitions, persistent store document formats, or your business domain entity designs. Instead, you should leverage encapsulation such that the resources your API defines and the internal details of your application can vary independently from one another. Remember, REST is all about state, not behavior. This is the key thing to remember about REST. The things you represent in APIs designed using REST architecture should all be nouns, not verbs, and as such, there is not really a place for remote procedure call or RPC style endpoints if you are following REST. Let's consider some different approaches for triggering behavior. In an RPC style interface, you might expose certain endpoints that allow external clients to invoke behavior on the server directly. For instance, a smart home API could allow a mobile device client to make a call to the service telling it to turn off the light. There might be other APIs exposed for turning lights on or changing their color, etc. Note that HTTP doesn't have any standard support for RPC. So, the server and client would need to agree on a protocol to use that was outside of typical HTTP standard usage. Post is frequently chosen since RPC style calls typically change the state of the system and are not necessarily safe to repeat, just like most post operation. Using a REST approach, however, the desired state of the resource would be sent to the server using an appropriate intention reveal HTTP verb. In this example, since the resource in question is a smart light bulb and it already exists, the put verb is the most appropriate one to use for this operation. Along with the verb, the new desired state is passed in the body of the request. It is up to the server implementation to determine how to change the state of the resource to the one that has been indicated in the put request. REST has a lot of good guidance for describing and organizing resources, but it doesn't try to invent its own way to manipulate resource state. Instead, it relies on existing HTTP standards for describing desired state manipulations. This is a good thing as it reduces a lot of design choices we might otherwise need to make. Instead, we can just follow standard guidance. Another option for dealing with long-running processes is to create a noun that represents the process itself. We can introduce something like a job, a process, or an operation and then use that as the resource that REST is representing. In this case, we could post to server a new job that we want the server to begin performing. The server in turn creates the job and returns back a location header where the state of the job can be monitored. Then, the client is able to pull that location to check what the state of the operation is. The server will continue to return a series of 200 OK responses while the job is not yet completed. The client may also have an option to cancel the job, assuming that the operation completes successfully. Then, eventually the server returns a result which includes the location of the operation's result. Then, the client is able to make a GET request to this new URI, which in turn will provide the output from the long-running operation. Whether you are using REST, parts of REST, or just designing your own set of APIs without any concern for REST, you should try to make appropriate use of HTTP verbs. Doing so will improve the consistency and ease of use of your API and may improve its performance and security as well. Browsers make GET requests to fetch web pages, and within most pages they also request additional resources using more GET requests. GET requests should be read-only, cacheable and side effect free. The second verb is POST, which web pages sometimes use to submit data using forms. Used properly, a POST request should communicate to the server that it needs to create a new resource with the information provided. To make updates to existing resources, the put verb is used along with a representation of the resource. It is expected that the representation be the complete state of the resource and not just a subset. To remove a resource, the delete verb is used. And if you wish to make an update to only part of a resource, you can use a patch request and only specify the portion of the resource you wish to update. You should avoid using these verbs in non-standard ways. If you design your API to leverage existing HTTP verb in a standard and consistent manner, your API will be easier to understand and more compatible with developer tools designed to work with APIs. Another occasionally used verb for web APIs is head, which is used to return just header data for a resource and can improve performance by preventing the need to return the entire resource. The options verb can also be useful as it provides a lightweight way to get information from the server about the kinds of requests the server supports. There are many more verbs, but these 7 are the main ones used for building and consuming web APIs. IANA defines at least 39 different verbs in its method registry if you are interested in learning more. The vast majority of web APIs only need GET, POST, PUT and delete. You may find patch, head or even options useful as well for certain optimizations. But you should avoid using less common HTTP verbs unless you have a compelling need to do so, as many API clients and tools are unlikely to support them, and many developers will be unfamiliar with them. In this course, we are going to focus on the 4 primary verbs of GET, POST, PUT and delete as well as patch. As we talk about these verbs, I need you to keep this phrase in mind. In the hypertext transfer protocol, idempotence and safety are the major attributes that separate HTTP methods. So what exactly are idempotence and safety in this context? Idempotence is a somewhat term that you probably don't use in everyday conversation. However, it is a concept that is useful to understand and apply in the context of web application development, especially for web APIs. RFC 2616, part of the HTTP 1.1 protocol, defines idempotence like this. Certain HTTP methods are said to be idempotent if, aside from error or expiration issues, the side effects of one or more identical requests are the same as for a single request. Idempotence speaks about the state of the system, not necessarily the response sent back by the operation. For example, a delete operation with a unique identifier will result in removing a resource with that ID if it exists, or doing nothing if it doesn't. In either case, the end result in terms of the system state is the same, even if those two operations were to return different responses. Wikipedia states that idempotent is the property of certain operations whereby they can be applied multiple times without changing the result beyond the first application. A good example of this property in the real world is elevator call buttons, which typically do not behave any differently if you press the button once or many times, even though sometimes it is satisfying to do so when you are in a hurry. Reading data typically has no side effects at all, so queries should typically be idempotent. In fact, queries are the special case of idempotent called nullipotent because they should have the same impact on the system. That is, no impact at all whether they are made 0 times, 1 times or many times. Unlike pushing a call button for an elevator, which has the same effect whether you do it one or more times. Looking at the clock has no side effects whether you do it 0 or more times. Methods that do not alter the state of the system should be considered safe for users to interact with. The convention has been established that get and head method should not have the significance of taking any action other than retrieval. Safe methods can be used by user freely, and any side effects they might have should not be considered the user's responsibility, since the convention is that such methods should not have any. Safe methods can be used by user without risk. They can also be prefetched by user agents to improve user experience and web application performance. Safe endpoints can be cached aggressively, since safe methods have the same effect on the system whether they hit the server or not. Think about which links on a website would be safe for the browser to prefetch or web spider to follow. Links to read or view other documents or pages are typically just fine. But clicking on links or buttons with labels like delete or buy now or checkout are probably much more likely to cause problem. Remember, idempotence means that the operations can be repeated without changing system state, while safe means that it does not change system state. Okay, so to wrap up, idempotence means it can be repeated without changing the state of the underlying system, and safe means it is not changing the state of the system. That gives us this simple reference table showing the different methods and whether or not they are idempotent or safe or both. Get requests should be read-only. They shouldn't change state. They should be repeatable and cacheable. Post requests create resources. They change state and should not be repeated, since doing so would create additional, possibly duplicate resources. Put requests put the system into a specific state. Making the same put request once, twice or many times should have the same impact on the system, but it does change state, so it is not safe. Delete, like put, should yield the same system state whether the request is made one or more times. It changes state, so it is not safe. Patch is just a more limited version of put and as such has the same characteristics. And head is another read-only operations like get, which should be both idempotent and safe. Review this table and be sure you know it. It will help a lot when you are considering which verb is most appropriate for a given operation you are designing. Post and put are similar in that they each alter server state and typically sends data in the body of the request. However, post is all about adding new resources, while put replaces the details of an existing resource. You should typically design your route so that posts are made to the collection resource and puts are made to the specific single resource. If you are generating keys on the server such as with SQL identity column, then your post request typically should not include the ID value in the root or the body. Your put requests need to specify the ID of the resource they are targeting, and they may do so in the root, the body, or both. Ideally, a put request body should include the entire state of the resource being updated, including its ID value. However, the ID used to look up the correct resources should typically come from the root, not the body. And assuming the ID exists in both locations, they should match. Otherwise, the client intention might be misinterpreted. Some systems will allow the changing of IDs. In that case, if the root contains one ID and the body contains another, then the system would attempt to perform an update that would include updating the ID to the new ID found in the body of the request. Remember, if you only want to update the part of the resource, the patch verb is more appropriate.
Now, let's look at the demo showing the use of these different HTTP methods on certain resources. I am going to use Postman tool. I have it configured using my localhost environment, so the host variable is going to be pointed at localhost 7094 port. When we go into this collection, you can see that I have a set of different verbs for post, put, get, patch, and delete for the author's resources. So let's start by looking at what happens when we make a simple GET request. Here you can see I am getting back some results. This is some test data for the system showing you different IDs and names and Twitter aliases. If I want to get a specific ID, we can go here and I can specify the ID as a key value in the path for this ID here. And here I am looking for author 2, so we will go ahead and send that. And you can see it works. We get back a 200 OK response with the payload. If I want to create a new author, I can do that. I can come into the post, can modify body to specify who that is. And then when I submit that, we get a 201 created, and in this case, it's showing us the body as well. But if we look at the headers, we can also see that it is giving us a location header showing us where to find this resource. It is under author 4. If I come back here and we change this to be authors 4, we should then be able to get that resource. We can delete a resource, same idea. Let's delete resource 4 that we just created. In this case, we get a 204 no content telling us it was successful. If we look at our full list once more, we should see that there is no resource 4 which we do. We can issue a put request to change how something works. So we can come here and change. We will say ID2 to be Rajan Kumar Arora and make sure that our ID matches here. And we will send that. And now we see the ID2 has been updated with that new value. Finally, we can issue a patch. A patch is a way to do a partial update. And so in here, we can specify that value we want to replace for a particular ID. So let's go back to number 2. And we are going to change that to make it so that the Twitter alias is .NET Coder. We will send this, and now you can see that we have updated just the Twitter alias on ID2. And if we see the full list again, ID2 previously just said string as its value, and now it has my name and .NET Coder is the Twitter alias. So that is just an overview of how the different HTTP methods should work with your resources and what the general CRUD operation should be implemented as using web APIs.
HTTP defines a number of status codes that are used to describe server responses to client requests. You should be familiar with the most common status codes and understand when it is appropriate to use them as part of your web API design. There are 5 classes of status codes. The first digit of each status code defines the class of response to which it belongs. The 5 classes of HTTP status codes are shown here. Class 100 codes are informational and in practice are rarely used. Class 200 codes indicate a request was successful with some variation in the details. Class 300 codes are used for redirection to indicate that the resource may be found elsewhere. Class 400 codes are used to describe various client errors including authentication and authorization failures. And class 500 codes are used to indicate server errors. The HTTP specification states that client must at least understand these 5 classes of status codes even if the specific flavor of code is not understood. Any unrecognized code should be treated like its base 00 code prefixed with that class first digit. Different operations typically have different status code responses. The key scenarios you will typically encounter are getting a resource, creating a resource, modifying a resource, and deleting a resource. Together, these 4 represents typically CRUD or create, read, update and delete operations. Additionally, you will need to consider security and permission as well as the possibility of unhandled exceptions. When fetching a resource, the success response is simply 200 OK. If the resource in question has moved, a 301 or a 302 code may be written. Note that unlike most browsers, API clients typically are not configured to automatically follow redirects. If caching is being used, a response of 304 not modify may be written to indicate to the client that their existing copy of the resource is still current. If the client requests a resource that does not exist, a 404 not found is typically written. And if a particular client has sent too many requests within a certain time window, the server may return a 429 code to indicate this. Authentication and authorization failures will have their own responses, which we will cover on their own. When creating a resource, typically with a post, the following status codes typically apply. 200 OK can be used when posting to get an access token since no resource is modified or created. You can also use a 200 OK if you intend to return the created resource in the body of the response. 201 created is the standard success response when creating a new resource and simply providing a link to its URI. According to the standard, the URI of the created resource should be written in a location header. 202 accepted is used for async processing. Responses should include a location header with a URI for an endpoint to poll. 204 no content may be appropriate if the post method does not result in a location that is identifiable by URI, though this is a rare in practice. 303 see other can use to point to the newly created resource functionally similar to a 201 created but designed to aid in caching. A 400 bad request is commonly returned in response to the malformatted requests, and 429 again can be used to enforce request limits. If you are using a put or patch, then a 200 OK is fine with no body or with the updated body. If you don't intend to return the resource in the body, then a 204 is more specific. Use a 201 if the put created a new resource, which will typically have the URI to which the put request was made. 202 accepted can be used for long-running processes and can provide a resource that clients can use to check the status. Use 204 if it was successful, but you are not returning anything. A URI can be in the location header field. You also specify a 400 bad request for any syntax or validation error with the operation. A 404 not found if the URI in question does not correspond to a resource the server knows about. A 409 conflict can be used to ensure that the client isn't modify a resource that has changed since the client last retrieved it. The payload should provide information to help the client recognize and resolve the conflict. And once more, you can use 429 for request limiting. When deleting a resource, you can return a 200 OK, a 202 accepted if you are going to perform the operation asynchronously. A 204 no content if the operation was successful and you have nothing to return. This is the most common case. A 404 not found if the resource does not exist or was already deleted, and of course a 429 to enforce request limiting. When dealing with security and permission, the most common responses types are a 401 if the client is not authenticated. If it provides authentication, the request may succeed. It should really be called 401 unauthenticated since that is what this status code actually indicates. A 403 forbidden means that the client typically is authenticated, so the server knows who they are, but the client does not have permission to access the resource in question. And a 404 not found, which can be used if the back end either doesn't know about the resource or does not want to reveal that the resource exists to the client for security reasons. For example, if you are trying to reach a private GitHub repository while you are not logged in, or if you lack permission to view it, in either case you will be told the repository is not found. If there is an unhandled server exception, the only thing you can return is a 500 server error, possibly with some reference information that will aid in diagnosing the problem from the server's log files. Be sure to return the proper class of status code when you have unrecoverable error on the server. Do not return error responses in the body of responses that otherwise have a 200 OK or similar success status code. APIs that do this are notoriously more difficult to program against because every so-called success response must be inspected to determine whether or not it was in fact successful. Now, let's look at some examples of the proper use of HTTP status codes. We are going to return to where we left off with the demo on HTTP Verbs. But this time we are going to focus on the status codes that are being returned. For example, when we post a new author, we saw that we got a 201 created. And if you mouse over the 201 created in Postman, it will tell you what this response means. And type of 2xx code, of course, is going to represent success. Any type of 2xx code, of course, is going to represent success. So, when we do a GET request and it is successful, we get a 200 OK. And the same is true when we do a delete and we get a 204 no content. All of these are telling us that the request was successful, but what happens if the request isn't successful? Let's look at an example where we try to create an author, but we are not going to provide it with a name. And it might be that the name is actually required. So here is the body of the request. We will try and create one that does not have a name and send that. And you will notice that we get a 400 bad request response. In this case, it is telling us that the request cannot be fulfilled due to the bad syntax. The client has made a mistake that is making it so the server cannot process the request. Now, I am using some built-in ASP.NET Core features to do a model validation, and one of the nice things about that is it will format those errors in a way that is nice to send back to the client. And so, you can see in the response that I have the information that the client would need. In this case, stating that the name field is required. You can do a lot of things with data annotations, as we will see later in this course, to make it so that this model validation and the responses that you send back are very informative to the client. And you absolutely do that. Now, I have modified this endpoint so that any submission will create an exception. So when I send the new response here, a new post, if I provide it with the proper values, what we are going to see is a 500 internal server error. This is the message that you want to return if there is a problem where an exception goes unhandled on the server. Do not use a try catch to capture this problem and then only show back a 200 response to the user. You definitely don't want to have your error message come back in the disguise of being a success status code. That will cause countless problems for your clients. So, 500 internal server error is the appropriate response when there is an exception on the server that you can't handle. You don't necessarily have to show the exception results here. In this case, they are being displayed because I am running in developer mode. But in your production API, this 500 internal server error should not display any significant information to the user. Instead, it should maybe just provide them with some correlation ID or error code that they could then use to look up information later about the source of the problem or to help the developer diagnose the issue. But while you are developing locally, it can certainly be helpful to allow the developer exception information to be rendered for you. Alright, so that is just a few of the quick, most common responses codes and how you would use them inside of your web API. ASP.NET Core has built-in types and helper methods to assist with returning different kind of responses. In ASP.NET Core MVC, there are three main return types that action methods support. First, you can return a specific type like an entity or a list of entity. Second, you can return an iActionResult interface. Or third, you can return an action result of type T, which is generic type. And of course, in all these cases, you can return an async method that returns a task of this type. Specific types can be primitive like integers or string. They can be complex types like data transfer objects representing an author, customer, order, etc. They can of course be collections like lists, dictionaries, arrays, or simply IEnumerables or even IAsync enumerables of type T if you prefer. A benefit of returning a specific type is that it is strongly typed, so it is easily understood by automated documentation tools like Swashbuckle or NSWAG, which can generate a Swagger document. Of course, it is also very simple to simply return the type that you are expecting to come back from your API. The biggest downside is that you cannot easily return any other response code or type. Now speaking specially about async. When we are talking about IEnumerable returns or any type of collections that might be written over an extended period of time, There is a definite performance benefit that you get by not buffering that entire list on the web server and then sending it over the wire. So, if you have the opportunity to use async enumerable, this will allow you to avoid that buffering and just send each individual item as you received it. Here is an example of what using async enumerable might look like. When you return a method that is async enumerable, the method must be marked as async and should return individual instance using the yield return keyword combination as shown here. So it is going to return individual product instance one by one as it receives them from whatever data source it is using. One operation that is supported by this scenario is the application in-memory filtering or business logic. As you can see here, we are doing a check to see if product is on sale before choosing whether or not to return it. Normally, filtering is better done closer to the data source, but sometimes it will make sense to perform it in your application. And this will provide a way to do so without buffering the result in a collection before you return it. And again, this can be important for performance as well as keeping the overall memory footprints of your application down to a minimum. If you choose to return action result, it is more flexible return type that was first introduced in the early versions of ASP.NET Core. It works with the built-in helper method that are exposed by the base controller class available in ASP.NET Core MVC. When we think about action result, in addition to being able to use the built-in helper methods, you can also standardize on this so that you have a consistent return type that you use for every action method. However, it does have the drawback of not being strongly typed. So, if you want to use a tool to generate Swagger documentation, you will typically need to add attribute to inform Swagger about what you exactly might be returning. Here is an example of an action method that returns an action result, and because it is not strongly typed, the produce response type attribute must include the type being written. In this case, author DTO. When you open this up in Swagger, this is what the attribute allows Swagger to display as the response expected for this endpoint. If you decide to use the action result of type T, result type, it supports returning objects directly, as well as the use of the built-in helper method. It kind of offers the best of all the worlds, and because of that, it is the recommended result type to use for just about every scenario. As you can see, it provides a combination of the benefits of using action result and specific types. The only real downside left here is that you may still have to use produces response type, unlike if you were just returning a specific type, but you won't have to specify the type. So here is an example of what that might look like. In this example, we are using an action result of author DTO. And so we can specify that this return a status code of status 201 created. But notice that in the attribute, we no longer need to specify the type of the object being written. That can be inferred from the action result's generic type parameter. In this case, author DTO. Minimal APIs offer a slightly different set of abstraction from ASP.NET Core MVC. They introduce a new iResult interface which is similar to iActionResult. They also have the ability to return specific types or just raw string or JSON result. If you are using iResult, it offers many built-in options for common use cases, which is similar to how the action result types are supported by ASP.NET Core. Now, let's look at some examples of response types as well as how they are represented in Swagger by default. We are going to look at some controller actions for this and show what the different type of responses will render in Swagger. Each one of the endpoints is going to be named based on the return type that it has provided. So one of these is getObject. Another one is getObject where it actually returns null. Then we can return a string. In this case, we are going to return JSON as a string. They are all basically returning a sample of a book. We will see that in just a second. We can also return a JSON result with the book. We can use an iAction result or we can return an action result of T. The data is simply a book DTO with an ISBN number a title and an author. When we go ahead and run this code, it will generate a Swagger document that we can use. You can notice from the Swagger document that we don't have a whole lot of information about what is being written in most of these cases. So, when we go to get an object or null or string or JSON or even iAction result, there is no information here about what is returned, and we haven't added any additional attribute to tell Swagger what those return types might be. But without even doing that, the strongly typed getActionResult of t does show us what is going to return back. Now one thing that we could have is something that actually returned a book DTO, and that would also have given us that strong typing. But for reasons we already covered, we don't want to do any of those other types because they don't allow us to return a 404 not found response or any other appropriate result type if we don't want to just return the actual object that we are expecting to return back. A couple other reasons to notice is when we return an object, we do get it serialized as JSON result by default. It comes back as a 200 OK, and the content type is set to application JSON. If we return null from an object, however, we don't get anything back. When we execute it, we just get a 204 no content. Notice that the content type is not set at all because there is no content. There is no body of the response. So some clients that expect to always have JSON, and maybe they are expecting to get back an empty JSON result in the case of null, might be thrown off if you are returning back a no content. When you return a string, you do get the data back that you would expect. And here is our JSONified data of the book. But notice that the content type here is text plain. So when you are returning a string by default, it is always going to come back as text plain, which again may not be what you want. If you are trying to get a JSON result, this will work as expected. And you will see the content type is application JSON. That is going to be the case when we return the same thing using our iAction result. And you will see here it is identical 200 response with content type application JSON. And finally, when we do application iAction of result t with the same thing, we get back the same result, the biggest difference being the documentation that you get in Swagger. That's all using controller based APIs. Of course, we now also have support for minimal APIs. Let's take a look at what that would look like. In the case of a minimal API, we can map a response like this. In this case, it is just mapping it directly to the object coming back from the entity. In addition to defining APIs inside of your program.cs using map get there is also a number of packages you can use to put those API endpoints into their own classes, which is my preference. One that I am using here for the author create endpoint is called minimalapi.endpoint. Using this package, your classes needs to implement the iEndpoint interface, and that is going to then give you the ability to set these two methods, the addRoot method and then the handle method. Obviously, the root is where you specify how you are going to wire things up to your actual endpoint. And then in the handle async, that is where you are going to do the actual work of the request. Now notice in handle async, we are using a task of iResult, which is the recommended approach when you are using minimal APIs. And when we are returning that result, we are using results to specify what we want to return, and since this is a post, we are creating a new endpoint. We are going to specify that it was created. We are going to note the URL where you can find the new resource, and we will also return back in the body the newly created resource as well, just so that we can save an extra round trip for the client that is using the API. When we look at what this is going to generate in the code, here is the generated code from the minimal API for that post. We can try it out and see what happens when we go to create it. One of the things that I want you to notice is that it is strongly typed, so the schema for the request includes the create author request, and for the response, you can see it is the author created response. Those both appear down as well in the list of schemas. Now, when we try this out, if we specify a name and an alias and run this, what we should get is a new resource, in this case ID 5. And also you will notice that it is provided us with a location header specifying that it is also available from author 5. This should give you a pretty good understanding of how to use the different responses type that ASP.NET Core offers, whether you are using controller-based MVC style action results and I action results or action results of T, or if you are going to use the new iResult interface with the minimal APIs. In this module, we quickly covered the principle of REST and how they apply to web APIs generally, even those that don't fully embrace REST features such as hypermedia. We learned about resources, which can be anything you can represent with an identifier, and how to design our web APIs around resources and their representations. Next, we learn about HTTP verbs or methods with a focus on those most often used by web APIs. We learned which verbs should be designed to be idempotent, safe, neither, or both. Then we learned about HTTP status codes, again focusing on those mostly commonly used by your web APIs. We learned which status codes are most often used and which ones belongs with which verbs or methods, as well as few things to avoid. Finally, we saw how ASP.NET Core provides features to make working with response types easier, such as iActionResult, action result of type T, and for minimal APIs, iResult. Up next, we will dig into web API models and how best to design them. I hope you will join me. In this module, we are going to take a look at best practices and considerations for designing the models used by your web APIs. The models we are talking about here are the things your API accepts and returns over the wire, typically serialized as JSON or perhaps XML. Let's get started. In this module, we are going to start with some basic best practices for your web API models. Then, we will introduce and talk a little bit about the robustness principle and how it applies to web APIs and the models you accept and return. Then, we will discuss how to decide what data your API should return depending on context. And then, we will look at some of the characteristics of good web API models, as well as some anti-patterns that might indicate your model aren't as good as they could be. Let's get started with the basics of web API models. The most important takeaway is that your web API models should almost always be DTOs. So, what is DTO? A DTO is a data transfer object. Data transfer objects are objects that have no behavior, only state, just properties, and no encapsulation. Many people confuse this with POCOs, which is another acronym. A POCO is a plain old CLR or C# object. DTOs are POCOs since DTOs generally just inherit from system.object. But not all POCOs are DTOs since a POCO could have methods and therefore behaviors. Why should your API models not have behavior? Because their only purpose is to be serialized and deserialized into the text format, which is then sent over the wire. At a minimum, your model's type should be focused purely on transferring data. That's it. That's their sole responsibility. Make sure they are just DTOs. To define your model DTOs, you can use C# record types or classes. Record types can work for many situations and often require substantially less code. Remember that even though your model objects don't have behavior, they can still include annotations to support model validation. Model validations is built into ASP.NET Core MVC controllers that use the API controller attribute. So, you should certainly take advantage of this feature when you can. If possible, resist the urge to just define a small set of DTOs. Name them each entity whatever DTO, customer DTO, order DTO, etc. Instead, wherever possible, provide your model types with intention-revealed names. Name is hard, but you can make it easier if you use something like create author request instead of just passing around an author DTO for every single one of your method in your web API. For DTOs that are used to create new resources, I like to name them something like create resource command or create resource request, replacing resource with the name of the resource. In this example, you can see that it is a class and it includes 3 string properties: name, address, and mobile number. Because it is a DTO, there is no encapsulation. That means there are no protected internal or private accessors. Everything is public. And because it is used for creation and the server is generating the keys, there is no ID property. Even though it is a DTO, we are able to add annotations from the system.componentmodels.data annotations namespace. We are using this to mark the name property as required and to specify maximum length for each property. Because we use constants to define the data model lengths, we are able to reuse those constants here, which ensures that they stay consistent. If you prefer, you can use records for your API models, which can result into much less code. In this case, it doesn't look much shorter, but that is only because of the annotations that are being used. When you don't need to use annotation, especially for your response types, records can provide a much more good way to define your models. When designing the models to use with your web API, you should keep in mind Postel's law, also known as the robustness principle. It applies to systems that must inappropriate with one another. Postel's law states be conservative in what you send, but be liberal in what you accept. It was coined by John Postel, who used the wording in an early specification of the TCP protocol. In practice, this means that when your programs call out to other programs, they should accept interface exactly, but when other programs call your program, you should accept requests that aren't perfect as long as their intent is clear. Applying this to web APIs, what you accept are HTTP requests and what you send are HTTP responses. You should take care to standards and specification and your own documentation with anything you send, but you should be more forgiving with what you accept in order to ensure your APIs are easy to use and bend a little before breaking over time. The robustness principle is often credited with much of the success of the protocols that underlie the internet. Although your services may not have the same reach as TCP/IP or IP protocol, you can still apply the same principle to the benefit of your services and their clients. The related law in Hiram's law and the importance of Postel's law become more clear when you couple it with Hiram's law for APIs, which states that with enough users, regardless of what you might commit to in your contract, all observable behaviors of your system will be dependent on by somebody. The more consistent and constrained you can be with your responses, the less likely you are introduce breaking changes to some of your clients. As an example, let's say that I want to change how I accept a Twitter alias into my APIs. Let's assume that the API has been in use for a while and the data in my system now has alias in a variety of formats. Some use an @ prefix, some don't, some include the full URL. So my solution is to try and fix this problem with data coming in different formats, might be to apply stronger model validation. Unfortunately, if I go this route, I am going to break clients that are already assuming one of the other formats than the one I pick. Here is an example of how I can enforce a rule stating that each of the submission that match the format of @ and then the alias name. I am using a regular expression here. This would certainly break existing clients that aren't expecting to use the @ prefix or which have sending URLs. Using a regular expression data annotation also doesn't provide a very user-friendly error message. As the saying goes, when you have a problem and you try to use regular expression to solve it, now you have two problems. If you do need to validate your model, you will definitely want to provide a better error message to your user than the one shown here. If we want to follow Postel's law and Hiram's law as well, then assuming we are already shipped a version of the API that allowed for multiple formats of Twitter alias to be provided, then we should continue accepting all of them so long as we can make sense of them. Then we can transform the known set of formats into the format we wish to use in our domain or persistent model. Once we have this in place, the API works as it always have for consumers and accept a wider variety of formats without breaking any clients. Essentially, it continues to work the way it always did, but we get the advantage of cleaning up our data and making it so that going forward we have data consistency. Here is some simple code that could meet the requirements. It is not designed for speed and could certainly be optimized, but it would be clear that there are 3 acceptable formats of Twitter aliases which can be transformed into the @username syntax. Obviously, you would apply this to whatever types your model might use. A common one is physical street addresses, which may be represented earlier on in an API's life as simple string, and then later on you might add more complex types with separate properties for city, state, etc. Being able to accept types in multiple formats will make your API easier for more clients to use generally, and avoid breaking those clients that used an earlier format will keep your API working longer. As you think about your API design, one key thing to consider is what data each individual API should return. It is very easy to create an API that returns too much or not enough data from the client's perspective. First, if you are only building one or a few clients that you control and you are able to make updates to both your clients and your API in simultaneously as changes are made, then don't think too much about what data to return from your API endpoints. Let the client needs dictate that you should return and aim to return exactly that the client needs, no more and no less. Following this approach will maximize the fit between your API and all of its clients and minimize waste, both developer waste as you try and build the right thing, as well as waste during the use of your system in terms of how much data is being retrieved or sent over the wire. It will also make your task of designing the API a whole lot simpler. You want to avoid returning too much data if the client only needs one record or one part of a large record. Then return a huge collection of large fully hydrated objects is wasting a lot of computer and network resources. Of course, you don't want to return too little data either. This often results in the clients having to make many more calls than would be optimal in order to get all of the data it needs. How many API calls should a given screen of your client of your API needs to make? Think about that for a second. Ideally, clients shouldn't have to make any APIs to get the data for a given screen. Making 0 calls will increase the speed and reliability of the screen in question dramatically. One obvious way to achieve this is not to require any data, but another is to leverage caching and local data storage options so that in many cases the data a screen might require is already on the page or on the client device at least. For screens that need data and the necessary data isn't already local, the ideal number of API calls to make in order to populate the entire screen is 1. If you have only one client that you are building a backend to support, you can optimize your API to fit its needs. If you have a bunch of APIs and a bunch of clients, you can still get the benefits of designing your API to suit each client by following the backends for frontends or BFF design pattern. When following this pattern, you should structure your API based on what your client needs and when it needs it. It is likely that any given screen the client needs to display will have certain data requirements, and this may need to come from a variety of resources in your backend system. Consider creating a single endpoint the client can call that will provide all of these resources in a single response rather than forcing the client to make numerous calls. Don't expose endpoints to the client that he doesn't need. Keeping your web API surface area small makes it easier for client developers to work with your API and improve security. Whenever possible, perform the necessary data aggregation on the server and then provide the exact data the client needs in as few API calls as possible. For a general purpose or public API that will have numerous unknown clients, you typically want to define both summary and detailed representations of each resource. You can return a summary representation when you are returning a list, and then you can use detailed representation with individual resource responses. Another consideration for collection is how you will support filtering and paging. Filtering usually doesn't impact the model, but paged response may, and you should define a standard format for this. For resources that have relationships or sub-collections, choose what to do with them in your summary and detailed representations. For a detailed representation, typically, you will include at least one level deep of your sub-collections. But here too, you might consider whether you need paging if those collections are large. Another approach that can minimize the size of the representations collection is to provide them as URI along with the paging support. Here is an example of GitHub public API with a partial list of what you get when you view a user representation. Notice that instead of include all of the user's followers, there is instead of followers underscore URL property which points to an API endpoint that would allow you to get all of the followers. Expanding the followers underscore URL, you get that list of followers once more with summary record not detail. By default, 30 records are written at a time, but you can provide query string parameters to page through the data. Note that GitHub's API does not include pagination information in its data representations. Instead of putting paging information in the representation itself, inside the response DTO, GitHub uses header to provide navigation links. By contrast, the harvest time tracking service API returns page information as well as a link as part of the response document itself. As you can see, there are different options to consider for how you want to expose paging and other metadata as part of your model or as a part of a header or some other way that you wish to communicate that to the client. As you can see, you will need to make some decision about paging which may affect your model types. The first question is whether you will support paging at all. If not, you can probably skip the rest of the questions, but if your API's result sets are large, it could result in performance problem. I recommend you to support paging from the start. The next question is, if you want paging data to be part of your response model and written in the body of your responses, alternatively, you can return paging metadata and links in response headers. My recommendation is to use response headers like GitHub does. This is supported by web standards described in RFC 5988 as well. You will need to decide on some default values for starting page numbers and page size. Most APIs I have encountered default to page number 1 for the first page rather than using a zero-based index in default page size between 30 and 100. If you don't have a preference, I suggest starting with 1 and 50. I also recommend you to be consistent across your entire API. Don't choose different page sizes as your default for every different collection resource you expose. It will just make it harder for clients of your API to have a consistent experience. Finally, you will need to come up with the standard names for your variables. I recommend page and per_page as these are clear and fairly common. Another common choice is to use offset and limit. If you do choose this naming convention, your offset should start at 0, not 1, for the first page of results. Let's consider some characteristics of good API models. We will start by looking at 4 characteristics of good models. First, they should be well named. This can be difficult. Naming is hard, but it is not the most important thing you need to consider as part of your API design. It will impact both models and your URIs. Second, your API model should be well factored. That is, each representation should be separated from others such that they are cohesive and as loosely coupled as possible. The resulting models should be well sized. Strive to include the right amount of information in each model. Obviously, this will vary depending on your domain, your clients, and a host of other factors. So, it does require some thoughts. Finally, try to get your model to be stable. Changes to your API model should be rare and, if absolutely required, should ideally only involve adding data, not changing or removing it. One way that you can get more stable, more well-sized and well-factored model is to use intention-specific model for different operations such as doing a new instance of a model versus a modification to a model. When we talk about well-named models, they should use resource names that clients understand, not internal names if there is a difference. They should not reveal internal architecture such as database concern. They should avoid unnecessary suffixes like DTO. It is okay in your C# code if you want to refer to a certain model as a DTO, but don't let that be exposed to the client of your API. Models do not map directly to the resource representations may use suffixes that can help to make their intent more clear, such as request, command, response, or result. Finally, consider how your names are going to be used. Names are frequently used both on the server and in documentation tool like Swagger. For instance, to create an author, you might have a C# type called create author command that's on the API, but the client might not see that. They might just post the endpoint as a bunch of JSON and they never actually care what the name of the type might be in your C#. They just supply JSON that corresponds to its properties. The name is true for the response or the result in most cases. Well-factored models avoid mixing too many concepts in a single representation or resource. Instead, large concepts are separated into distinct resources. When a resource includes several closely related primitive type fields, it often makes sense to leverage objects for this. For instance, a line segment might need 4 values to represent its start and end points. This could be 4 separate primitive fields at the root level, or there could be 2 points objects, each with an X and Y fields. When breaking resource up, avoid one-to-one relationship where possible. There is usually a more suitable way to split up large resources. One exception to this is summary versus detailed representations, but remember those are actually representing the same resource. They don't really have a one-to-one relationship. Many different but related tiny models will require a very chatty interaction between clients and server. So, you want to avoid having models that are too small. But large models with many sub-records, which may in turn have many sub-records and relationships, can be very resource intensive. You want to aim for a Goldilocks size that is just right for most clients. And if you only have one client, then obviously make it suit that client. One common approach to this is to use summary records in list and detailed records for individual representations. This is so much common that you can think of it as a best practice. Provide clients with size limiting tools like paging and filtering, as this can also help to right size the amount of data that you are returning. Your most used resources and their associated models should be the most stable elements in your API, since they are going to be the thing that are dependent on by the most of a number of clients and the most parts within a client. Where possible, make changes in an additive fashion to avoid breaking your clients. And if you have more than a single client, consider versioning upfront as part of your API design. When you do make breaking changes to your models, be prepared to support clients as they migrate to the new version. Now, let's consider some Web API models antipatterns, or things that you typically want to avoid when designing your models. Some common problems in model design including choosing non-standard names for things like IDs, paging links, or resource names that clients don't understand. Another common occurrence that usually impacts teams who have a more data-centric view of software will be API models that are just a little too close to the database tables they are wrapping. Make sure clients of your API remain unaware of how your data might be persisted. Keep your database naming practices out of your API models. Obviously, once you expose an API and clients are consuming it, you want to avoid changing it out from under them without notice and without providing versioning support. While you should absolutely make some efforts to size your model appropriately, you should also provide some mechanism that allow clients of your API to control the size of responses. This would include things like filtering and querying, as well as the ability to drill down into more detail by using less verbose models in list response than in individual responses. Finally, regardless of the decision you make about how you are going to design your resources and API model representations, make sure you will be able to provide some kind of documentation for your clients. Provide an interactive testing tool like Swagger with Swashbuckle, or just provide written docs, or both. But in any case, make sure the docs are clear, complete, and current. Imagine you have a blog engine and you expose an API to view its post. Here is what that might look like if you use the WordPress blog engine database schema directly as your API models. A few things to note here: ID is capitalized, JSON typically uses camel casing and would use a lowercase id. All other fields are lowercase, not camel case. They are using underscores for separator, pretty much just with their prefixes. By the way, all fields except for id have a prefix, and most of this could be omitted or made part of a camel cased field name. There is no relationship in the JSON schema to post author, and it's not described as an ID in any way. It is just there as a number, and there is no relationship in a JSON schema to comments, just their count. This may be a useful optimization, but ideally there should be some information on how to load the comments themselves too. Remember that going between a relational data store and a document format like JSON requires some thought. Make sure your models in the JSON or whatever format the client works with may be XML still. Make sure that those models should work to the standards and convention of that wire protocol format. Here is one way the previous example could be improved. Names are now using camel case as the standard convention. Unnecessary prefixes have been removed. Links to resource URIs are in place instead of just numeric keys with no additional information. All of these improve the model compared to the obviously DB-centric one that we saw in the previous slide. That's it. Let's review what we covered in this module. First, we look at some basics of Web API models. Remember, they should be data transfer objects and should only include the data needed for the operation in question. Next, we reviewed Postel's law, the robustness principle, and we also took a look at another related law, Hiram's law. Keep your API usable for the long haul by following these principles. We considered how to structure the data that our API returns. We learned about summary versus detailed representation and options for paging and navigation large resource collections. We wrap up by looking at some characteristics of good Web API models as well as a few antipatterns that you will want to be careful to avoid. I hope you enjoyed this module and learned a few things along the way.
Well, hello, Rajan here. I would like to thank you for diving into the first 90 minutes of my Udemy course on ASP.NET Core Web API Best Practices. If you found value in this snippet, you will love the full course, where we will see into advanced topics like Web API implementations best practices in ASP.NET Core, Web API security best practices, testing ASP.NET Core Web APIs best practices. Are you ready to take your skills to the next level? Enroll in the complete course on Udemy using the link in the description below. Let's unlock more knowledge together. If you like this video, please do share, like and subscribe to my channel for more such videos. Thank you and see you in the next video.